So in this problem, we're asked to find the volume of a solid of revolution given the following. One function, y equals 1 over x plus 1 square root, y equals 0, x equals 0, x equals 3, and the area between all these functions that's rotated around the line y equals 0, and this is just the x-axis. So to start, I'm going to write everything in function notation because that is where it is most useful. So if we write here our y equals 1 over x plus 1 square root, we can write that in function notation. That's f of x equals 1 over, and instead of writing this in radical form, I'm going to write it in with an exponent of 1/2 because exponents are generally more useful than radicals. So our other functions, y equals 0, well that's g of x equals 0. X equals 0 is h of y equals 0, and x equals 3 is j of y equals 3. And all of these are still rotated around our axis of revolution, y equals 0. This we don't convert into function notation. So next, we need to determine which method we'll be using to find the volume of this solid. And because this f of x is the most complicated, we're going to be using this. We're going to be using f of x, g of x, and our axis of revolution is in terms of y here. And so these two variables have to match. That's why we use g of x and not one of our functions in terms of y. We used g of x, f of x, but our axis of revolution is in terms of y. And because of this, because these two are the same and this one's different, we'll be using the disk method. We could use the shell if we changed this function to be expressed in terms of y, but we're not going to do that. We're just going to go ahead and use the disk method here. And to do that, the first step is to set our two functions equal to one another, like it is in any solid revolution question. So if we say f of x equals g of x, well that's 1 over x plus 1 square root equals 0. And this is never true. And to prove this is never true, let's multiply this to the other side. And 0 times this is still 0. So this turns into 1 equals 0, and that's never true. So these two functions never cross one another, so we're going to have to look elsewhere for our domain. And where we're going to look is we're going to look back at the original equations that we were given, in that we converted x equals 0 to h of y equals 0 just so that we had everything in function notation at the beginning. But we can go ahead and convert that back into x equals 0, and this one we convert back into x equals 3. And this is going to be our domain. Our lower bound is going to be 0, and our upper bound is going to be 3. And we can write that as x is a member between 0 and 3 inclusive. So our next task, now that we have this domain, is to find which of our two functions is greater given this domain. And this would be a step that we would do whether we were doing the disk method or the shell method. And we would do it the same way because I'm not an advocate of using graphs to solve math because I would like to rely as little on technology as possible. And so I'm going to use algebra to solve this. And I'm going to do that by finding a test point C, which is between 0 and 3 and not including 0 or 3. And I'm going to find a point between here, and it could be any point between here. I chose 1 just for simplicity's sake. And I'm going to plug this C value into our function. So our function f of x was 1 over the square root of x plus 1. So plug c, which was 1, into this. We have 1 over the square root of 1 plus 1. Well, that's just 1 over the square root of 2. So if we look down here, that's just 1 over the square root of 2. Our g of x value was 0. So we have g of x equals 0. So it doesn't matter what we plug in here, we'll always equal 0. So g of c equals 0. Using these two values, we can construct an inequality, saying that f of this c value, which is in our interval, is greater than g of that same c value. Sorry, I nudged the camera. So now that we have this, we can broaden this inequality into f of x is greater than g of x over this interval. And that will be true because we chose a point within that interval. And so because we're using the disk method, we have to broaden this one step further. If we were using the shell, this would be enough. But because we're using the disk, we have to broaden this to include our axis of rotation value. And our axis of rotation value, if you don't remember, is y equals 0. So we're looking at how these functions compare to that number 0 here. And our f of x is greater than 0 over this interval. Our g of x is equal to 0 over this interval. So we can construct this inequality, where f of x is greater than g of x is greater than or equal to, in this case it's equal to, our axis of revolution value, which is 0 over this interval. So now that we have this inequality set up like we need to, we can continue on. And the reason we had to include this axis of revolution in this inequality, in the disk method, and the reason we don't have to do it in the shell method, is because in the disk method, we need to determine which of these two functions is farther from this axis of revolution. And so we have to tack this on either on the right side or the left side. So it's either going to be less than or equal to all of these or greater than or equal to all of these. And so this allows us to construct two functions, capital R of x, which is our outside function, and lowercase r of x, which is our inside function. And if we were to look at this on a graph, this function f of x would be farther away from our axis of revolution over this interval. This is just saying that only numerically, and our g of x will be the closer function over this interval. And so we can say that our outer function, f of x, minus our axis of revolution value, which was y equals 0, so f of x minus 0 is this, 1 over x plus 1 to the 1/2, minus 0 is just 1 over x plus 1 to the 1/2. That is our capital R of x function. Our lowercase r of x function is just g of x minus our axis of revolution value. So g of x is 0, axis of revolution is 0, so 0 minus 0 is 0. So now that we have these two functions, we can construct our formula for the disk method, which is volume equals pi, not 2 pi like in the shell method, but one single pi, times the definite integral from 0 to 3 of our outside function, capital R of x squared, minus our inside function, lowercase r of x squared, times dx. So from here, I'm going to plug in the functions we just got. So we have capital R of x is this, and lowercase r of x is this, which is just 0. So I'm going to plug those in. Nothing else happened there. And then I'm going to simplify. So this 0, it doesn't matter that it's squared. It's going away. If we distribute this squared to the inside, we have 1 squared is just 1, but this x plus 1 to the 1/2, when you raise an exponent to an exponent, you multiply exponents. And so 1/2 times 2 is just 1. So this is 1 over x plus 1 times dx and, integral and all that. And so you can use substitution here, but you don't really have to if you can recognize that the derivative of x plus 1, well, that's just 1. And so we can just go ahead and integrate here and say that our volume equals pi times the natural logarithm of x plus 1 evaluated from 0 to 3. And these absolute value bars don't actually need to be there because we're evaluating from 0 to 3. There's no value of x between those two numbers that could make this inside expression negative. And so I put the absolute value bars there because you put them there regardless, but we don't actually need them in this case. It doesn't change the value of anything. And so from here, there's no way to actually simplify that. So I'm going to go ahead and plug in my numbers here. So if I plug in 3, so I have natural log of 3 plus 1, should be a minus here. It doesn't actually matter, but it should be a minus the natural logarithm of 0 plus 1. We did it again. So if we continue this, we have 3 plus 1 is 4, 0 plus 1 is 1. Natural log of 1 is just 0. E to the 0 is 1. And so that's why this addition or subtraction didn't actually matter other than correct notation. So this is going to cancel away, but this ln of 4 is some god-awful number, and so this is going to stay, and it's going to be multiplied by pi. So our final answer, because this is 0, is just pi times our natural log of 4.